This lab, we will be observing constant motion and using the momentum principle to describe and observe our findings. The momentum principle states an object's final velocity is equal to its initial velocity plus the net force divided by the mass of the object times the change in time, or delta t. From there, we can use the position update formula to find the object's final position. The object's final position is equal to the initial position plus the velocity, which we found using the momentum formula, times delta t, the same delta t that we used to find the velocity. To demonstrate the momentum principle, we will be using a real-life model and a computer simulation to demonstrate it. Our model is a toy car weighing approximately 0.732 grams. We will be pushing it across a table at a start position based on where the axis is located in tracker, at a start position of negative 0.179 meters on the x-axis. We assume the center of mass is just below the mirror of the car. We then push it across the table, ending the tracker right before it hits the box. We then take this data and put it into an Excel sheet. In addition to the real-life model, we will be using a GlowScript program to demonstrate a computer model of this in action. There are two main areas of the code we want to focus on. The first section is lines 31 through 40. We know that the mass of the object is 0.732 grams, so we enter it on line 32 right here. Our initial conditions are found from our tracker file. Our initial x position is negative 0.179 meters, so we enter that here. Now, we do have to do a little work to find the initial velocity. So what we do is we take the first two position points from our tracker data, and then we do x2 minus the first x, and do the same for the time, and divide. With meters on top and time on the bottom, seconds, we get 1.71 meters per second as our initial velocity. We go back and plug that in for our initial x velocity in the positive direction. We also start at time equals 0, and we use a time step of 0.01 seconds. This is just for precision. The second section of code we want to look at is lines 49 through 70. These lines are a while loop that constantly updates the object's position and velocity until it hits a certain time that we designate. Here, we designated time is less than 1 second because that is when our tracker data ends. First, we want to calculate the net force, lines 53 and 54. If you look back at our original formulas here, you'll notice that if we want this to be a constant motion problem, or a constant velocity problem, or in our first equation, the second half will somehow need to equal 0. But how do we do that? Well, the object is always going to have a mass, so that can't be it. And the delta t is always going to be changing. So the only way to do that is to have a net 0 force. So looking back at our code, we enter 0, 0, 0 to simulate a 0 net force. In lines 56 through 60, we apply the momentum principle, which is the formulas we discussed at the beginning of this video. In line 58, we use the velocity formula, where the ball's velocity is equal to the ball's velocity plus the net force divided by the mass of the ball, or in this case, the car, times delta t. Well, if you look back at lines 54, since our net force is 0, 0, 0, the ball's velocity will always stay the same. But each time through the while loop, it's still going to calculate it. We then move on to line 60, where the ball's position, or again, in this case, the car's position is updated using the velocity times the change in time. Well, this will always change because our velocity is never 0. However, the velocity is never changing, so the position will move at a constant rate. When we run this program, we get a straight line on the position versus time graph, a straight diagonal line with a constant slope. On the left, we have our tracker data. On the right side of the screen, you can see the results from the GlowScript program. Here, you can see both data sets plotted on this graph. Both of them have the same initial starting position, and both have the same final time. As you can see, our GlowScript program, which is the orange line, is a constant slope all the way to the end. However, our observed line, which is the blue line right here, has a slight curve to it, ends at a position slightly less than the computed time. Why is this? Well, for one, if we look at a free body diagram for our car moving across the table, we can demonstrate that the car is moving towards the right. And because of this, there's a friction force pushing towards the left. This friction force from the tires on the table is what slows the car down. What if, instead of using x to the right as the positive direction, we used x to the right as the negative direction? Well, not much would change. Our graph would look slightly different as the data would point negative instead of in the positive direction. In conclusion, we learned that using the velocity update formula and the position update formula, both of which are derived from the momentum principle, can be used to demonstrate what happens to an object's position and velocity with an x amount of net force. In our case, it was 0, so we noticed a constant motion and constant velocity in our computer model, and a similar result in our physical model, varying slightly because we could not negate the results of friction in our model.